is to simulate in a laboratory setting the conditions, as the theory says, of conditions that might have existed on an Earth 3 to 4 billion years ago. Now, in principle, there's nothing wrong with this approach. However, in order to get experiments that work, you have to constrain the conditions so that you can get results. Even the design of the original Miller experiment illustrates this. He arranged the flask in one way and no results. And you rearrange the glassware and you get results. So it was, why were the results, why do we consider the arrangement that gave results that set of conditions which match the early Earth instead of the other one? Well, it's because the one set of conditions, the glassware, gives results that matches the theory. Now, that's fine. Then you have to go on and consider, well, what else are you doing in this simulation experiment that corresponds with what you say existed on an early Earth?
Isn't it rather impressive that amino acids were produced in the Miller experiments?
Well, that's what was so impressive to many off the bat. You take a simple environment of methane, ammonia, water vapor, and hydrogen gas. No oxygen in these systems, by the way, because according to the chemical evolution hypothesis, oxygen would only appear on the scene after the first life began to produce oxygen. The first plant life would have produced oxygen. And then you can do these experiments without oxygen there because you're dealing with it prior to the beginnings of life. At least that's the idea. It turns out there's a practical benefit of doing this. You don't get experiments to work if you have oxygen present because oxygen is a poison preventing these type of chemical reactions. Another thing is that if you use methane and ammonia, in other words, the so-called reducing environment with some hydrogen gas present, you can get plenty of organic materials produced. And yes, it was very encouraging to the proponents of the theory when amino acids, a few amino acids were discovered in the flask. In fact, over the years, more than a dozen such amino acids have been found in the Miller-type experiment.
How close is the development of amino acids to the threshold of life?
Well, you have to have many things besides amino acids. And if you only produce the suite of amino acids that are necessary for living things, and there is a subset of 20 amino acids that we know in living things, you need those, but you need many other compounds and chemicals. But let's just deal with the proteins or the amino acids as their components first, because in these simple experiments, simulation experiments, you produce not only that set of amino acids, but many other amino acids. There are far more amino acids that are produced, and even in greater abundance than are produced of the 20 amino acids. And so you mix all those together with all of the other chemicals that are being produced, and you find out that the interfering cross reactions of these just prevents any type of meaningful buildup of chemicals that are sufficient to go on to the next step in making life. So it's a very difficult, almost intractable problem, I would say, chemically.
What are the steps involved in producing proteins from amino acids?
Well, the way typically these experiments are done, you do an experiment, you produce a glycine, an alanine, and a few other amino acids that we know exist in living systems, in true proteins, for example. And then you isolate those amino acids from the system, and you purify these amino acids, and then you use these amino acids separated, isolated from the myriad of other chemicals that would have been present in a, quote, prebiotic soup of chemicals. And then you you react these amino acids together under other conditions to produce polymers. In other words, you're trying to build up, see if you can simulate the production of a protein.
Why are amino acids isolated during this process?
We want to separate the chemicals from each other in different stages of simulation experiments so that we can get a realistic handle on how the developmental process of chemical evolution occurs. If you don't do this, you have all the different chemicals mixed together and they will mutually interact and react with each other. Now, why this is bad, or what happens is, amino acids will combine with amines or other groups that have say a carbonyl group, and you will get dead end process. You won't get meaningful substances.
What do you get?
Just a goo, just other substances that don't have any biological significance to them. And this is the really difficult part in trying to conceive how to do a simulation experiment. It's well known, nearly every one of these experimenters know that you can't do a realistic experiment according to what the theory says and get meaningful results. But if you just did that, everybody would get the same glop, and it's not a meaningful result. And so you have to have meaningful results to publish, and that's the reason why you separate things. So you can get have an idea of how you're going step by step to produce, to go along the process of making life.
How can the investigator affect the outcome of a simulation experiment?
Well, you must have, in any kind of a simulation experiment, the role of the investigator. I mean, it's impossible to do experiments without the investigator. So when we wrote our chapter on the role of the investigator in these simulation experiments, we were trying to point out and make a distinction between those legitimate interferences in the experiment, such as stopping the experiment at a certain time and withdrawing sample for analysis. That's legitimate. You can do this. The experimenter can set up the laboratory conditions and set the parameters of the experiment, and that's fine. These are the kinds of investigator role that you would expect. What is illegitimate, and we felt like needed to be brought to the attention of students and other professors who were investigating this, and brought it out into the open, because, believe me, it's never brought out into the open. You can go to these international meetings, and there's two things that are almost never brought into discussion. One is the problem, as we've already mentioned, the role of these interfering cross reactions. If you discuss the role of the interfering cross reactions, there would be no other place for the conference to go. You would just focus right there. It would stop. There wouldn't be anywhere else to go, because you can't have any meaningful results. So nobody talks about it. That's frankly the way it is. The other thing is that besides the interfering cross reactions, you must not talk about in these conferences the role of the investigator to interfere in an illegitimate way with results, because if you did, it would become obvious that most of these experiments are unacceptable according to their own criteria for what we're doing is prebiotic simulation. That means, by the way, let me explain what I mean by that. According to the theory, we want to reproduce in a laboratory setting conditions that would have been on an early Earth 3 to 4 billion years ago, and that means no interference from God or any other outside forces, and either then or since. So we make a naturalistic assumption from the beginning to the present. Well, that means then that we cannot have, if we're going to simulate those conditions, we cannot have an investigator constraining the conditions that are outside the boundaries of what we've already said were acceptable for that prebiotic Earth.
How did you evaluate the different chemical evolution experiments?
Basically, we put the scale in such tentatively drawn. I mean, if we can show that it fits the parameters of a legitimate prebiotic experiment, then yes, by all means include it. And we'd be glad to move our line one way or the other according to how the data goes. But so far, the experiments are such that the investigator's role prejudices the outcome of the experiment in an illegitimate way. I just find it intolerable that men of science can allow this to go on and not make it vocal and not make it open, and certainly not, be more specific in their research papers. As I mentioned earlier, though, the reason why we don't do it, why it's not done, is that if you did, you wouldn't get meaningful results. And you can't publish a lack of results. You can't just do a research paper and say, well, I'll publish a paper of what I've done the last 2 months that hasn't worked. You've got to have some results. And it turns out that in 40 years of all these experiments, by and large, now there are a few exceptions, but by and large, most research papers have fit the category that we would call illegitimate, because the experimental parameters are constrained in such a way, the conditions are constrained in such a way that it would not fit a prebiotic earth.
Well, the Oparin-Haldane hypothesis is the most general theoretical framework within which experiments and research on the origin of life are conducted still today. Oparin proposed his chemical evolutionary views for the first time back in the 1920s, and Haldane right at the end of the decade of the 20s. And essentially the hypothesis says that on the primitive Earth, before any life was present, you had carbon compounds in very simple form in the atmosphere, in the form of methane, for example, and other simple gaseous substances, and that these would gradually increase in complexity under the influence of energy provided in the natural environment, solar ultraviolet flux, for example, cosmic radiation, heat energy. And then you would get the transfer of these molecules, somewhat more complicated molecules, down into the oceans, amino acids and sugars, for example, and then these would link up later on into polymers, polysaccharides, proteins, and then you could have nucleic acids forming. Then you get protocells from aggregation of these materials. They would compete by a kind of proto-natural selection process, a proto-Darwinian process, and the one that would win that competition for dwindling nutrition in the oceans would be the first to arrive at the state of a full living cell. So it was a process of very gradual complexification of carbon compounds, taking maybe hundreds of millions of years.
What are the major underlying assumptions of the Oparin hypothesis of chemical evolution?
Well, there are a number of them. The first that I could think of was that Oparin thought that the ancient atmosphere was very different from our present air. It was a reduced atmosphere, and it did not have molecular oxygen in it at all. Typical gases were methane, ammonia, water vapor, and molecular hydrogen. Another assumption would be that the molecules that were formed in the atmosphere under the influence of these energy sources were somehow protected from destruction by those same energy sources, so that you could really have an accumulation of life-building substances, amino acids and sugars and purines and pyrimidines, could actually survive the rigors of the ancient environment. Once they got into the ocean, if they ever did, another assumption of the hypothesis would be that just the right what we call biomonomers, amino acids, for example, or sugars, would react with the same kind of biomonomer to give you the kind of polymer that is so characteristic of life, namely a polypeptide, all amino acids. In other words, no other substance would get in there and interfere with that clean production of polypeptides.
Are there any other important assumptions in origin of life theories?
Yes, there are other basic assumptions of the Oparin hypothesis. One of them, additional one, is that that just the right optical isomers of, for example, amino acids reacted with each other like all L amino acids, forming the first polypeptides, since we find exclusive currents of the L or left-handed form of amino acids in protein today. Oparin had to assume that there was some sort of process by which the L form would be separated out from the D form, which is equally likely to have been formed. We also have to assume, if we believe this is the kind of process that generated the first life on the planet, that the polymers that were forming in the oceans could have acquired genetic information. And this is a key point: specified complexity, genetic information in these polymers. They have to, the subunits have to line up in specific order in order for biological function to be possible. And yet we know of no chemical means for the alignment of these subunits in the absence of pre-existing genes. And of course, when we're going toward the origin of life, we certainly don't have any genes in the picture. So the question is, how can these substances align themselves? And so it's a major assumption of the hypothesis. Another one is that as you get close to forming an actual cell, that all of the many, many different components you need for a cell to live, all the different enzymes and the nucleic acids and the other substances and the metabolic reaction sequences, could all have originated simultaneously and in the same microscopic region of space, a bacterial volume. And the probabilities against that happening spontaneously would appear to me, do appear to me to be overwhelmingly negative.
How well are these assumptions supported by currently available scientific data?
Well, let's start with the assumption of the reduced or reducing atmosphere of the primitive Earth. I think that if we look at current geological data referring to the oxygen content of ancient surface minerals, we cannot decide the issue of whether the ancient atmosphere was reduced or not. But the evidence is consistent with the possibility that there may have been some oxygen present in the old atmosphere. Another reason for believing in the strong possibility of molecular oxygen having been present from the earliest times in the atmosphere is the fact that even today in the high atmosphere, water vapor is being photodissociated by the solar ultraviolet radiation, and the result is molecular oxygen and molecular hydrogen. Hydrogen is very light, could have escaped into interplanetary space, leaving that oxygen there, I think, from the very earliest times. So if oxygen had been present, even to the extent of only 1% its level, or 0.1% of its level in the current atmosphere, I don't think you could have had any chemical evolutionary development at all, because oxygen destroys organic compounds very effectively. So you could say that chemical evolution, according to the Oparin hypothesis, would have been extinguished right at its source, right at the earliest stages of its movement.
Maintained by disulfide bonds, van der Waals attractions, hydrogen bonds, and electrostatic interactions. So these are complex systems, very complex molecules, with lots of possibilities of how these could form. And these big proteins, these big things, they don't just spontaneously wrap up into the shape they need to be. There's other enzymes that act upon them that help these to fold. All right, regarding peptide synthesis, let me bring you back to this. But more importantly, the mineral surfaces could have acted as naturally occurring organometallic catalysts. We don't know how to do this in solution in the lab, to do anything cleanly. But somewhere under a rock or in an ocean, like it's presupposed here, this is all happening in water. It could have, it may have, possibly could have, and it perhaps only reacted with L amino acids. This is all fallacious. None of that is real. None of that happens. It's never been demonstrated, even in a pristine lab, under anything that is remotely related to prebiotically relevant, where you're just dealing off of a mineral surface. No way. And even if you use modern synthetic methods, we don't know how to do this well in solution. I mean, the buildup of material in there after each step, it just wipes you out. I mean, the buildup of material in there after each step, it just wipes you out.
You will get dead-end process. You won't get meaningful substances.
What do you get?
Just a goo. just other substances that don't have any biological significance to them.
I mean, the buildup of material in there after each step, it just wipes you out.
The really difficult part in trying to conceive how to do a simulation experiment. It's well known, nearly every one of these experimenters know that you can't do a realistic experiment according to what the theory says and get meaningful results. But if you just did that, everybody would get the same glop. And
I mean, the buildup of material in there after each step, it just wipes you out.
What is illegitimate, and we felt like needed to be brought to the attention of students and other professors who were investigating this and brought it out into the open, because, believe me, it's never brought out into the open. You can go to these international meetings, and there's two things that are almost never brought into discussion. One is the problem, as we've already mentioned, the role of these interfering cross reactions. If you discuss the role of the interfering cross reactions, there would be no other place for the conference to go. You would just focus right there. It would stop. There wouldn't be anywhere else to go because you can't have any meaningful results. So nobody talks about it. That's frankly the way it is. The other thing is that besides the interfering cross reactions, you must not talk about in these conferences the role of the investigator to interfere in an illegitimate way with results, because if you did, it would become obvious that most of these experiments are unacceptable according to their own criteria for what we're doing is prebiotic simulation. That means, by the way, let me explain what I mean by that. According to the theory, we want to reproduce in a laboratory setting conditions that would have been on an early Earth 3 to 4 billion years ago, and that means no interference from God or any other outside forces, and either then or since. So we make a naturalistic assumption from the beginning to the present. Well, that means then that we cannot have, if we're going to simulate those conditions, we cannot have an investigator constraining the conditions that are outside the boundaries of what we've already said were acceptable for that prebiotic Earth.
I mean, the buildup of material in there after each step, it just wipes you out.
The experiments are such that the investigator's role prejudices the outcome of the experiment in an illegitimate way. I just find it intolerable that men of science can allow this to go on and not make it vocal and not make it open, and certainly not, be more specific in their research papers. As I mentioned earlier, though, the reason why we don't do it, why it's not done, is that if you did, you wouldn't get meaningful results. And you can't publish a lack of results. You can't just do a research paper and say, well, I'll publish a paper of what I've done the last 2 months that hasn't worked. You've got to have some results. And it turns out that in 40 years of all these experiments, by and large, now there are a few exceptions, but by and large, most research papers have fit the category that we would call illegitimate.
I mean, the buildup of material in there after each step, it just wipes you out.
There's an interesting contradiction that comes in when you look at the stated assumptions about what the conditions on the early Earth were and what is required to make an experiment work. You have an early Earth, says the theory, void of any intelligent activity. I mean, that's by definition to do a naturalistic experiment. But in order to make the experiments work, the illegitimate role of the investigator, who is always intelligent, prejudices the direction or changes the direction over which it would normally go if that investigator did not do certain things. Now, let me give you a specific example here, because I think it's important for it to be understood how it works. The theory says that, for example, ultraviolet light would have been a major energy source on the early Earth. There's no reason to doubt that it wasn't irradiating the early Earth. So we want to simulate in our laboratory setting experiments using ultraviolet light. Now, in order to do the experiment, even with methane and ammonia present, you must use the shorter wavelengths of ultraviolet light. less than 2,000 angstrom units or wavelengths in order to make the chemical reactions take place to give us a product. But what happens if you use the longer wavelengths, say greater than 3,000 angstrom units? What happens if you use those? If you use those, say greater than 2,000 angstrom units? Well, what happens is that the destructive processes of the products begins in very big time. And so you're destroying the products of this reaction thousands of times faster than you're producing the products. So, in a laboratory setting, if you use the full spectrum, for example, of course experimentally you cannot do this. We don't have a way to get the full spectrum. But we can produce longer wavelengths and shorter wavelengths. But these experiments are never done this way. We filter out the longer wavelengths. And I say that's illegitimate.
Are there any natural processes that would have filtered out destructive ultraviolet light?
If, in fact, there was a realistic filtering mechanism, then of course it would be an acceptable experiment. But no one has suggested any way, any possibility, or any mechanism for eliminating the longer wavelengths and just allowing the short wavelengths to react with the materials. And I think that, frankly, it's done because it gives the results that we have already specified as a stepwise procedure toward the development of living things. And interesting thing was this, another factor that must be considered, I think. By the time a body of criticism in the literature of origin of life was built up, okay, to show that these destructive processes would have far and away dominated the situation. By the time this literature was built up, the assumption was already set and permeated the whole field. We can do it. The monomer level, in other words, the first level of making amino acids, is presupposed nearly by everybody. And so the fact these criticisms are unheeded. And so we've gone on now to explain, well, how do we make proteins? The first 10 years of the field, say from 1953 until, say, 1965, 66, almost all, the vast majority of papers during that time was, how do we make amino acids? How do we make adenine, one of the bases in DNA and RNA? How do we make the sugars, the monomers, because you can't have a DNA or an RNA if you don't have sugars? Well, despite all of the body of criticism that says, well, it's not very realistic that you ever had a prebiotic soup that had adenine in it or ribose in it, or that had very meaningful concentrations of these various amino acids from which you can make proteins. Despite that criticism, the field today has presupposed that we have granite to stand on. And they don't even have sand to stand on. And they're trying to build polymers, proteins and nucleic acids, as if we have solid evidential basis that the precursor or components on which to build these polymers has already been established. And it has not been established. So the field now is dominated, majority of papers are dealing with the polymer level. So we're in a different decade and we're doing different things, but it hasn't worked out.
What additional steps would be required to develop life?
In order to have life, you have to have not only the amino acids from which you make proteins, but and the nucleic acid, the various components to make nucleic acids, but you have to have the the assembly for the cell structure, cell membrane. And the cell membrane is not simply a bunch of fatty acids that react and make a micellar or a bilayer of chemicals, so that you can have an enclosed boundary. What has been discovered in the last decade about the cell wall, the cell membrane, to show that it is utterly complex, extremely complex. It's perhaps one of the major discriminating factors in allowing certain materials in and out of the cell. Now, this structure must be there in order to have a viable living system. And no one has any clue how to do this. There are many things of which we don't know how to put together, how to assemble it. But conceptually, the problem has been for the last 25 years to make the monomers and then see how to make the polymers, and then how to, and different research workers and groups are trying to work on different facets of the problem. But let's not kid ourselves. We're discovering more and more how utterly complex the living system is. And that's why the field is shifting and changing. We're either at the end of a paradigm where chemical evolutionary processes are being recognized as is the wrong approach. I mean, however much merit there has been seen in the past, we're rapidly approaching the age where more and more research workers are saying, well, we're going to have to try something else. We're going to have to do something else. Why? Because no results that are meaningful. There's not anybody in the world that can explain in a realistic way how to make a protein. There's not anybody in the world that can offer a realistic explanation for how to go step by step to make even a nucleic acid. And in a realistic environment now, with plausible conditions. And I have to put that qualifier in there, with plausible conditions, because people get Nobel Prizes for using constrained conditions, where you manipulate the conditions so that the chemistry only goes in one direction. But if you do this, that's no longer prebiotic. You see, that's the problem. We have to do it in such a way we can mimic a dumb, stupid nature, blind chemical, physical processes. Now, if we are going to require something of the level of a Nobel Prize winning scientist to manipulate the conditions, then you can do this with great difficulty to make some things, but still no one's ever made a bacterium. No one's ever made a cell of any kind. No one's ever made a virus, even. No one's ever made the kind of protein from just basic chemistry. Now, Fred Sanger and others have gotten Nobel Prizes for making, like, for example, insulin, but certainly this was not done with the kind of crude processes that the Origin of Life field is trying to use to mimic the process.
What is so difficult about making proteins or nucleic acids?
Well, the problem in trying to make a protein, for example, from even if you have just a pool of amino acids, is that the energetics is such that now it's an uphill process. Now, I mentioned before having methane and ammonia and blasting them with the energy and having it as a downhill process. Well, let's assume now all we have is a pool of amino acids that are the right set of amino acids to make a true protein. Well, how are we going to assemble the units, individual amino acids in a linear sequence to make a protein? In the first place, in a real protein, they're all left-handed amino acids, I guess you would call it, except for glycine, which doesn't have any handedness. But all of the other 19 amino acids are left-handed amino acids. Well, when you do the simulation experiments, you get a 50-50 mixture. Now, there's no way around that anyone's found. If someone could do a laboratory experiment and say that fit the conditions of something realistic on early Earth, where you just made left-handed amino acids, but this would be a tremendous encouragement to the field. In fact, that person would probably get a Nobel Prize. For example, if somebody can get a Nobel Prize for showing that an enzyme can have catalytic activity, then which is a requirement. What did I say?
RNA.
Yeah, RNA is now recognized to have catalytic activity. It's not just a part of the nucleic acid or part of the informational system, but it is recognized to do the role of, on a somewhat more limited level, of an enzyme. So if this could happen, and is worthy of giving a Nobel Prize for this discovery, then certainly anyone who figured out a way to produce left-handed amino acids would probably be worthy of the same kind of thing, especially considering the amount of work that's already gone into it. Now that's one thing. The other problem is linking them together. In a real system, you can't do it without having an enzyme present. In fact, the assembly process it can't happen without enzymes. And the reason being, you must have the energy put at the right place to make the reaction go uphill. And that's the problem. It's a tremendous uphill. It'd be the equivalent of, I guess, being down in a valley and trying to go to the top of a mountain. And this doesn't happen without not only energy. If you put energy if you have gasoline, you have energy, but you have to have it in the right kind of engine. I mean, you don't just pour gasoline over your some kind of some kind of a wagon. You've got to have an internal combustion engine to use the gasoline to drive you up the hill. That's what the enzyme does. It uses the energy that you have available and couples it to the individual amino acids to bring about the production of the protein.
In addition to the energy problem in protein synthesis, isn't there a sequencing problem?
Absolutely. In order to have viable protein, you must have the right sequence. And the reason for that, according to the standard way of looking at it, is if you don't have the right sequence, the protein doesn't fold up properly to give its overall three-dimensional structure. Best way I can describe it is that the overall three-dimensional structure is said to be held within the sequence of the individual amino acids in the protein. If you had the right sequence, the molecule would fold up. Okay, so I call this self-assembly. But you must get the right sequence. And you can't get the right sequence by just chemical processes that aren't directed. And they are directed in living system by the enzyme. But in a flask, they can be directed by the role of the investigator. So you can't get around the fact that either you have to have an enzyme or you have to have the role of the investigator. If you have the role of the investigator, that's an illegitimate entity for what you said is the prebiotic experiment. And that's the impasse this field has been in for some time.
Are DNA sequences analogous to a written language?
Probably one of the real emotional experiences, you might say, that I've had in doing this kind of work over the last 20 years is I used to have almost every biology book I've picked up and trying to explain how the DNA molecule works in helping to code for proteins, for example. How to make proteins by using amino acids. The explanation has been given in terms of the analogy to a written message. And of course, in terms of function, this is precisely what happens. And after, I guess, a number of years of reading the literature on these origin of life experiments and thinking about how they were worked out, and then focusing in on the role of the investigator and thinking about what the criterion is, or the criteria are for making successful experiments, and realizing how the enzyme works actually in the assembly process, and just figuring all of this together, and then being hit with, well, it's only a crude, superficial resemblance to a language. I mean, in reality, but it looks like one. But it must have been the result of just purely natural processes here. I began to see that as increasingly unrealistic. That it would be comparable to going to Old Man of the Mountain in New Hampshire and recognizing the face on the side of the hill, and then going to Mount Rushmore and seeing the faces of presidents on the granite and saying, well, these also were the same kind of superficial resemblance. Well, it's obvious. When you see it, you know wind erosional processes are not responsible for putting the faces on Mount Rushmore. To me, it's the same problem we've got when we look at the informational sequences in DNA. Most of my colleagues think this is purely rubbish, and they say this is the same kind of superficial resemblance as Old Man in the Mountain, and I don't think so. It seems to me that what we've got is that the requirements are too close and the similarities are too great for it to be just coincidence. So I'm very much impressed by this, and I'm still open to consider a purely natural process that can explain it, but I haven't seen anything that makes sense so far.
Has Hubert Yockey made similar claims?
Yes, of course, Yockey's paper did not actually make this connection. It was something he did say, though, that caused me to think more realistically about the idea that the information content is not just a superficial resemblance to a language. Here's what he said, if I could remember it exactly. He said that there is a mathematical identity in the structure of these base sequences in DNA and the alphabetical letter sequences in a message. So he's only talking about a mathematical identity of the structures of these two systems. Now, by experience, we know that it takes intelligence to arrange the alphabetical letter sequences in a written message. So if they're mathematically identical structures, it seems to me quite reasonable that it also takes intelligence to arrange the base sequences to spell out their genetic message. And that's the basis for this. And until I actually saw that written there like that, the mathematical identical structure, I don't think it ever clicked with me to get beyond the, well, this is just like Old Man in the Mountain. And until I actually saw that written there like that, the mathematical identical structure, I don't think it ever clicked with me to get beyond the, well, this is just like Old Man in the Mountain. And until I actually saw that written there like that, the mathematical identical structure, I don't think it ever clicked with me to get beyond the, well, this is just like Old Man in the Mountain. I now realize that what we have in DNA is more like Mount Rushmore.
All right, now I've got something very interesting to add. So for some people, it just doesn't click. It's so obvious once it clicks. But before it clicks, it's not obvious. Many things in life are like that, where it's right in front of you, but you don't see it until you see it. God wants to see those who are truly wise. And after they've realized the obvious, well, will you come and search for him? Because that which is precious but hidden ought to invoke your curiosity. And who is more hidden and what is more hidden than the Almighty? And what and who is more precious than him? But there's something I'm going to tell you guys that's going to make you guys just wonder. The carvings of the faces on Mount Rushmore are not like carvings of faces on a mountain. They are carvings of faces on a mountain, right? It's not like what it appears to be. It is what it appears to be. And it doesn't just appear to be that way. It is that. The DNA code is not like a code. It is a code. And like the doctor we just listened to, Dr. Thaxton, he said it wasn't until someone said something which made it click in his head. But like for the world's most proclaimed atheist, like I keep mentioning, Anthony Flew, for him, as soon as he saw the DNA and what it did, it clicked. But now here's the interesting thing about the DNA. There were two people who discovered the DNA together. One of them was Francis Crick, right? The other guy, I forget his name, but the one I remember is Francis Crick. The reason why I remember him is because the DNA functions as a code, right? But Francis Crick was a code breaker in World War II. A lot of people don't put these things together, but I'm gonna I can't let this stone go unturned. Okay, I can't keep it hidden. I'm gonna tell you, Francis Crick was a code breaker in World War II. Who knows that Francis Crick was a code breaker in World War II? God. So, since the DNA functions as a code, it's not like a code, it is a code. Since that's what it does, it would take a code breaker to realize its value and what it does. So, since God caused a code breaker to discover the DNA, when they first discovered the DNA, it didn't click in the code breaker's head. It didn't click in Francis Crick's head that this functions as a code. They knew that it was what was responsible for the cell, so much so that at first glance, they said, oh, we know what made a cell. It wasn't God, it was the DNA. See how God plays tricks on them? So they said, we know what made the cell. It wasn't God, it was the DNA. And then several months later, after investigating what the DNA does, because Francis Crick was a code breaker, hence why God is using this man, because this is a very specific work of art, this trade, a code breaker in World War II. There are not many people like that in the world. And then what are the odds of a code breaker discovering the DNA, okay, which functions as a code and will take someone with that type of mental savvy to understand it? So at first glance, when they saw it, they knew its value, but they didn't fully comprehend its value. And then Francis Crick, as he kept working on it, several months later, he realizes, wait, no, this thing functions as a code. Yeah. So will you really be stupid to say that that's just mere coincidence? Okay. Yeah, okay. So remember, it's not like they knew it was a code, and so they said, let's go and look for a code breaker to come and discover the DNA. Because, no, come on, people. The two people discovered the DNA. What they did in their past is of zero relevance. They're just two people who happened to fall upon the DNA. They discovered the DNA, right? Like someone who discovers gold, right? But then let's say someone discovers gold and he happens to be a goldsmith, but it wasn't through his goldsmithness that he discovered the gold. He just happened to stumble on gold. But coincidentally, his work of art, his trade is a goldsmith, right? A code breaker discovered the DNA, but he didn't discover the DNA because of doing codes. No, his past work in the World War II has zero connection to how he discovered the DNA. He just discovered it along with somebody else. They just, they're working with the cell and they discovered the DNA. Then lo and behold, they find out that the DNA functions as a code, that it is a code. So now, hold up, wait. You mean to tell me that the DNA is a code? But what are the odds of the DNA being a code and me being a code breaker in World War II? And me being the only one who has the mental savvy, wherewithal to understand that this is functioning as a code. You see? So it took a while for the French, the Germans, the Chinese, the Japanese, people across the oceans in England. It took a while for them to verify that no, this this thing is a code. Yeah, but the one who first discovered it, he didn't realize it at first, but because he had the mental wherewithal, he had that background, it clicked a lot faster for him. So much so that it took a while for other people to understand it because they're not code breakers. So what are the odds of God? Let me not say, when it comes to God, there are no odds. So God used a code breaker to discover the DNA because it functions as a code. It's not a coincidence. It's not a coincidence. All right, continue with the video.
In the mystery of life's origin, you refer to order, randomness, and specified complexity. Could you give us an overview of these concepts?
Yes, it's very important to make the distinction between order and complexity, and then between complexity and specified complexity, so I'll do that. A random situation is something that you can use, for example, with a sequence. Just pull letters out of a hat at random, and then the sequence would be a random sequence. This is what you would get if you do in the simulation experiments and you made a polymer. There might be some crude ordering. Some people are very impressed with the slight ordering tendencies that natural laws would give in sequencing these things. But of course, it's not like order that you have in a crystal. So an order would be like A, B, A, B, A, B, A, B. This would be a sequence of order. And a random sequence would be like A, J, B, Q, T, something like that, where each letter, you might have a run of 3 or 4 that are consecutive A, but in the long run, each one has equal or near equal probability of appearance out of the sequence. Then a specified sequence is one that has like a written message, T, H, E, D, O, G, the dog, and then spell out in the sequence, the dog ran. This is a sentence that's spelled out, fits the vocabulary, fits the grammar, and the proper syntax. It is this kind of distinction that you can recognize as a way for order, and then randomness, and then specified complexity. Now the thing is that in the examples are that the results of stochastic chemistry, what happens in a lab, in a flask, is an example of a sequence that would be random. Complex is a random state. Order would be like a crystal. Everything is specified in a particular sequence, a defined arrangement. But specified complexity, it's complex. Some have said this. It's like a random situation where it has certain rules that are like language rules. So it's not a totally ordered arrangement like A, B, A, B, A, B, but it fits the characteristics of a language. And we see that in a language system, but the same thing happens with the DNA and protein. It also happens with making, for example, making a computer, or anything, artifacts, or other examples of specified complexity. Mount Rushmore would be an example of specified complexity. In fact, you don't find examples of specified complexity except the structures of artifacts that people make, and DNA, protein as examples.
What do you think the presence of specified complexity in a living system indicates about its origin?
In terms of the origin of specified complexity in living systems, I would say that if we had any examples available that unrestrained or unconstrained natural processes produced specified complexity, then I would be prepared to go along with the community of scientists that are saying that natural processes produce living systems. But we don't have anything like that. Every single example of specified complexity we have is either an artifact produced by a human being, or else it is the result of the living system. And so, like the structures of DNA and protein fit the pattern of what human beings produce. One way you can look at it, it's easy to understand why for so long people have used the analogy that a human being or a living system is like a machine. The machine analogy to living systems has had a long record now. And it's been very productive in a lot of things that have been accomplished in scientific approaches.
All right, now this here is very, very, very important. Just like Mount Rushmore is not like carvings of faces on a mountain, it is carvings of faces on a mountain. Just like the DNA is not like a code and does not function like a code, it is a code. So too, the cell. Think about the human body. The cell, the most simplest living cell, does not function like a machine. It is a machine. But this is the critical thing. Many people, when they hear the more educated people who have come to realize that these things are created by someone with hands that we just can't see him, but clearly he's there and he's hidden himself for some unknown reason, which I know the reason. Hopefully you know why. The reason why they use these analogies, like when a tornado blows in the junkyard, what are the odds that it can assemble a Boeing 347 plane and a jet engine? And what are the odds that if wind blows on a pile of bricks, it can assemble a building with inner wirings and rooms and sheet wall and canvases inside and TV sets? And these things may seem like a joke to you, but there's a reason why they give these analogies. The reason why these analogies are perfect analogies is because the molecules that makes up a cell are no different than the molecules that makes up a machine, a building, an airplane. You see, the problem with you lesser educated ones is this. You think that the molecules of a cell are different from the molecules of a car. You think because the molecules of a cell are now in motion and they're gel-like, right, and semi-fluid-like, that they're different from the molecules of a car. Protein, fats, lipids, carbohydrates, nucleic acids. These are molecules. You know, what makes up steel, what makes up bricks, what makes up gold, what makes up sand. Like James Tour said, give me a second. A lot of distractions. Like James Tour said, computer chips, silicone chips, sand is made out of silicon, right? But sand will not, you give it, no matter how much time you give sand on the beach, no matter how much forces of nature acts upon it, it will never create a silicone chip, right? It will never create anything that even resembles that complexity of a silicone chip, right? But the molecules of a sand are the same molecules of proteins, fats, lipids. They all do nothing, like James Tour said, like all chemists say. Well, not all chemists, because some play stupid. But the honest chemists will tell you, molecules just lay there. They don't do anything. Without, like, this is quoting James Tour verbatim. He says, without an already existing biological entity, which means a living entity, without a biological entity acting upon them, molecules do nothing. They don't self-assemble. There's no magic, enigmatic thing that they do, that sometimes they do this and create some complex thing. No, they just sit there like sand on the beach forever. Like he says, forever. They do not move. They're not going to somehow create silicone chips. But you see, there's a higher chance of sand forming silicone chips than forming biological things, because biological things break down faster. They get corrupted easily, which is why a living system needs a membrane to protect itself, an exoskeleton, a skin, something to protect itself from the environments. A silicone chip can be out there and it's still strong. It's durable. It will last longer. But yet even that can't happen. So how can something as sensitive as life be created in a dirty environment? The first living cell needs to be in pristine, clean conditions. How do you get that in a dirty environment? Right, so, okay, back to the point. These are molecules. Can you imagine the molecules of bricks self-assembling to create a brick? Can you imagine the molecules that makes a brick now form to create a miniature microscopic building? That's absurd. You can't picture that. So you got proteins. Okay, amino acids, right? And they form proteins. But these things do not move. Fats, they do not move. Carbohydrates, they do not move. So how is it that they organize themselves into factories? How is it that they organize themselves into factories? How is it that they organize themselves into a car? How is it that they organize themselves into a steel factory, into a building? Make it microscopic. I know, see, this is the thing. You think of these things in larger terms because a building is huge, but a living cell is microscopic, right? No. The things that makes a cell, those are all the same molecules that everything is composed of. And everything just sits there. It doesn't move unless biological entities come along and moves them to craft them. Whether they are grand or microscopic is the same thing. It's the same thing. You see, you have to understand these things. You have to understand that even when it's microscopic, as a matter of fact, it's more difficult to do it microscopically. That's why engineers have a term that the more ingenuity you can put into something and make it microscopic, the more efficient it is. Because imagine you make technology that's so microscopic, you can compound upon it and make amazing things. But that's very difficult to do. It's almost impossible. God has done it. That's why a cell can live. That's why humans can function the way we are, because we are trillions of microscopic factories within ourselves, which compounds to make, a cell, a cat, a rabbit, a lion, and a human being. Molecules do not move. They do not self-assemble. They just sit there. And the moment anything biological can come along, anything organic can come along, it will degrade. You have to preserve it, take it away from the very same environment that you crafted it from and preserve it. Otherwise, it will be polluted. And the chemical reactions create other unwanted chemicals that just...
So you see, God could have taken any material, any molecule to make life. He didn't need to choose only this set of molecules. Fats, proteins, carbohydrates, nucleic acids. He didn't need to use those set of molecules. He could have used any set of molecules. He could have used steel, the same molecules we use to make our machinery. He could have used those same molecules. Why didn't he use those machineries or those sets of molecules to make his machinery that he wanted? Because friction, it won't be as efficient. Common sense, the molecules that he chose to use to make life is far more efficient for movement and motion and longevity in terms of movement and motion, as far as these things are concerned, in relation to harder, more friction-based things, right? Understand something. If these machines are made, whether it's based on whatever molecules, fats, proteins, steel, metal, iron, gold, it doesn't matter. All these molecules, whatever machinery is made through whatever molecules you make, it is just a machine. It will not move unless it gets energy. And even if it moves because of energy, that movement will not be motivation based. It will not be movement towards a target. It will just be a movement for movement's sake. It will just be moving, but it won't know what it's moving towards. It doesn't even know it's alive. It doesn't have self-consciousness. It'll be like a baby that's alive, and maybe it can walk, crawl. It shouldn't be able to even crawl yet because that's later advanced. That's more advanced. But let's say it's crawling. It's just crawling, and it will just bump its head into something. It will bump its head into something and it will be there. And it'll just keep, like a robot that's hit a wall, but it just keeps moving towards that wall. And it's not going anywhere because it's just moving towards that wall. It's just stuck there. That's what you would have. You would need to give it something that the molecules can't give it. Yeah, the molecules, let's say for argument's sake, has given it, the molecules, let's say for argument's sake, has given it mobility, motion, because of energy powering it, right? That motion, how is it even able to, why is it put together in a way where it can move, walk, and a bacterial flagellum shaped just like an outboard motor, the same way humans will make it? Why is it even built like that? Why would molecules self-assemble that way? But okay, again, we're just saying, okay, fine. It would not know what it's moving towards. The molecules will not give it that. The molecules will not give it a mind. Mind supersedes the molecules of the brain. That's you understand? The molecules of life, even though, yes, amazingly, they form these molecular machines, it's still nothing. It would be nothing unless something above the level of molecules gives it intelligence, so that the molecules, this machine, would know what to do with its machinery, would know where to go, what to do to preserve its life, because it doesn't even know that it's alive, to preserve a life that it doesn't even know that it has. It doesn't know that this is something special that it needs to preserve. It doesn't know, it doesn't care, it's just going to die.
But the machine never arrived at by spontaneous equilibration of chemistry and physics. These forces must have certain boundary conditions in which they operate. And this is what human beings do to make artifacts. We can make machines ourselves, but we don't find machines arising by natural processes. The same situation. So I would say that really we haven't progressed much in terms of our understanding about this question. So I still conclude that the data supports the position that specified complexity is somehow, whether we like it or not, a result of intelligence.
Okay, the last thing. It's just so many examples I want to give you guys for it to click, you know. What's the difference between the molecules that make up me and the molecules that make up this, or the car that I was sitting in? You see, like the chair behind me, the glass behind? Why don't they move? Forget that they can't even self-assemble to become a door on their own, unless a biological entity is acting upon them to craft them into a door. But why can't it move? Why is it just sitting there? Because that's what molecules do. That's what molecules do. They just sit there. So why am I moving? Why did the first cell? Why did the things that come together to make a cell? Why did they move? They're just molecules. And you say energy. Okay, so but I'm not gonna get into that. Let's say the energy gives them the energy, and they had the means to utilize that energy into useful energy, so that they could move. Okay, fine. Let's supersede that and say, okay, fine. Why are they connected in a way where they can afford to be moved? You understand what I'm saying? Why are they put together? This door is attached to the wall, right? But why is it attached to the wall? It can't just because the door is there and the wall is there, and you put them together, doesn't mean that the door is going to stay next to the wall. When wind blows, the door is going to fall. Why is it attached to the wall? Because you see, there's something that connects them, right? That thing that connects them, it took energy to be able to connect those two entities together, those two assemblage of molecules together. The enzyme that puts a protein forms, that door is an assembly of proteins, right? Okay, fine. You say the door can assemble, proteins can assemble by themselves, or amino acids can assemble by themselves to make a protein. Okay, fine. The amino acids, the molecules, are self-assembled to make that door. And then the amino acids self-assembled to make that wall. Okay, fine. But for this protein to assemble with this protein, the door to assemble to this wall, you put them next to each other, they're not going to stay together. So you need a catalyst. You need an enzyme. Now energy is involved for that catalyst. That enzyme needs to take energy from the cell. So not from nature. It takes it from the cell. So it needs to be an already living system. It takes energy from within the cell, namely ATP, and the ATP synthase. Anyway, the machinery of that, oh my goodness, that came about by chance. Yeah, all right. So the enzyme needs to take the energy from the ATP and combine them, just like a human would craft and use fire and a chisel and things to bind them together. That's what that enzyme does. But the enzyme needs to be shaped specifically, which in itself needs to be crafted a specific way. Just like a tool, a hammer, or anything needs to be crafted specifically to be able to combine these two things together. And it can't be combined just anyhow. It needs to be combined very specifically. Okay? It needs to go to the exact spot where it needs to connect, where they can be connected, and connect it there. It can't just connect any place. Why is it connecting them? Why? Why is it connecting it at the exact same place where it needs to be connected to actually serve a function, a useful function? If it connects it in a place, if the door is connected at the top of the wall, you can't open the door this way. You have to open it this way, but it can't open that way. So you have to connect it exactly where it'll be useful. This is just in simple terms, but understand, like, the more you understand the complexity of these things, the more it's absurd to say that it happened by chance. Now for the cherry on top. Imagine all these molecules after they've been assembled. Two things. After they've been assembled, one, there is a record of how to assemble them stored in the DNA. There is a record of, you see how the enzyme connected the door to the wall, and how the door was made and how the wall was made, right? There's a record, a lab book of how it was done and how to do it again. Molecules, keeping a record of how they constructed their construction so that it can be done again. And when the door begins to chip, it's broken off, deconstructed, and rebuilt again. The same process, so that it could keep being. I said two things, right? So that's one. It kept a lab book of how it was done, how to do it again. Second, it replicates into another building. These are just molecules, okay? The car, the building, the cell, all made of molecules, replicates into the exact same thing. If it's a building, it replicates to another building. If it's a car, it replicates to another car. If it's a cell, it replicates to another cell with 99.9% accuracy. What that means is all the wirings of the building, all the doorposts, all the doors, all the nails, all the TV sets, all the cable connections, all the ACs, so that the system doesn't overheat, all the things, all the plumbing system, so that it can expel things, all the things the doors, so they can ingest things, all the securities, all the security components, so that it knows what can go, so they can discriminate what can go into the cell and out of the cell. All of that was replicated 99.9% accuracy. That's natural to you. So so these molecules self-assembled, impossibly self-assembled into these complex machines, and then it kept a lab book of how it did it so that it can do it again. And then it replicates all the trillions of components and the set up, all the pillars that are there in the system. It replicates it into another identical system with 99.9% accuracy. No, it didn't redo the process again from scratch. No, it just took a copy of itself and replicated it. It just whoop, made another Sammy, made another Samuel, made another David, made another Hannah, made another Diana, made another Angela. Just molecules. Yeah, okay.
Is naturally occurring organometallic catalysts. We don't know how to do this in solution in the lab, to do anything cleanly. But somewhere under a rock or in an ocean, like it's presupposed here, this is all happening in water. It could have, it may have, possibly could have, and it perhaps only reacted with L amino acids. This is all fallacious. None of that is real. None of that happens. It's never been demonstrated, even in a pristine lab, under anything that is remotely related to prebiotically relevant, where you're just dealing off of a mineral surface. No way. And even if you use modern synthetic methods, we don't know how to do this well in solution. I mean, the buildup of material in there after each step, it just wipes you out. But somewhere in the ocean, it figured it out. Moreover, it was said nucleic acids, proteins, these are utterly trivial to synthesize. We even have machines that do it for us. Some suggest that
Jim is constantly talking about how we don't know how to make the 4 classes of biomolecules, which are nucleic acids, proteins, carbohydrates, and lipids. This is ridiculous. Nucleic acid synthesis and protein synthesis are utterly trivial.
Utterly trivial. Utterly trivial. Then why do people buy all their reagents from companies that isolate their reagents from nature? If it's trivial, why don't they just make it? No, because it's very hard to make these compounds, and it's very hard to hook them up. Why do they need such machines? Why not just dump it in a flask or dump it in the ocean? They'll hook it up for you.
It's so easy to do that we even figured out how to make machines that do it for us. We type in the sequence we want on a computer, let the machine run, and we can get a DNA strand of any sequence of nucleotides we want, or a protein of any sequence of amino acids we want.
Yeah, sounds so easy. Shocker. Some have said
any biomolecule is easy to synthesize.
Wow. Just remember that, synthetic chemists, I know you're having heart palpitations now, that somebody would make such a claim, that there's people out there that really believe that. Why don't you guys just quit your job? Why don't you men and women who work in synthesis just quit your job and we'll just have technicians make the biomolecules, because they're so easy to synthesize. Just trivial. And further said,
Jim knows this. He's a synthetic chemist. What he probably means is that we haven't seen these biomacromolecules form spontaneously outside of a biological system. But that's not what he says. He does not make the distinction, and this seems deliberate on his part.
Form spontaneously? Even in a biological system, these don't form spontaneously. Just poof, just form. None of this happens. In biology, you got enzymes very carefully putting these things together, and if there's a misstep, there's other molecules in there that take care of this. Nothing forms spontaneously like this. Nothing of any complexity forms spontaneously. No, I didn't know that, and neither does any other synthetic chemist. It's difficult for chemists to make most macromolecules, and usually impossible when restricted to prebiotic chemicals. And much harder for prebiotic Earth, where the Earth could not buy the 20 amino acids in homochiral form, or the carbohydrates, or the nucleotides, or the lipids. And no chemist in her right mind would support the nonsensical claim that any biomolecule is easy to synthesize. Here's what a protein synthesizer looks like. You have all these different vessels you have to have, and all of this plumbing that it's hooked up to. So to say we have machines and this is really easy, look at the research that went into this machine. This is a machine that was just designed in 2020. Now, we've had peptide synthesizers for 30 years, 40 years. But the sophisticated ones are just coming out, more sophisticated ones. This is not easy. You don't find this under a rock. And every one of the chemicals in here, every one of the amino acids in here is selectively protected on the nitrogen. Every one of them is if it has an active side chain, has a protection group on that. Every reagent here is highly purified, human-made, human-designed reagent. Every solvent is highly purified. This is not in a bunch of junk water. There's no water. This is all solvent-free, done solvent-free, done water-free. Why water-free? Because water hydrolyzes this. These reactions wouldn't go in water. But somehow under a rock, it figured it out.
On the screen here, I have a picture of DNA, which is a familiar molecule to most people, but it's made up of these nucleotides shown here. And each nucleotide making up DNA actually has 3 chiral locations. So you can have left or right in position 1, left or right in position 2, and left or right in position 3. That means there are 8 different chiral possibilities for each nucleotide. But in life, you have always the same exact chirality in every nucleotide in DNA and RNA. And the simplest forms of life have over 500,000 nucleotides in the DNA. So we're talking about, like, take a coin that has heads and tails, and you have to flip that coin a couple of million times and only get heads every time. Would you consider that natural? It's not a natural process. So this concept of homochirality, which means very consistent chirality, is very unnatural. It's not what you would expect from a natural process. It's just like you would not expect a perpetual motion machine from a natural process. How the molecules of life have consistent linkage, not just consistent chirality, but linkage. So on the screen, again, I have a DNA molecule, and this is what you see in every biology textbook. It's a familiar structure. And because you've seen it so much, you think, well, that's just how it forms, right? But it turns out that all of the components making up the DNA, the pieces of the nucleotides, they can attach to each other in many different ways. You can have hundreds of different wrong configurations, but life depends very much on a very consistent, perfectly arranged structure. So on the screen, I have just 4 examples of different structures for just 2 nucleotides. And in panel A is the correct form. That's the way it ought to look. That's the way life is based on. And then you have panel B, C, and D, which you can see are highlighted some changes where something goes wrong, and that will lead to death. That is not an option for life. So this, on top of the chirality, they kind of go hand in hand, but you have to have everything perfectly arranged. And we know natural processes just don't produce something with that kind of a consistency. To get a perfectly consistent 100 million components in a row is exceptionally unlikely. And even scientists today, you know, they can make DNA in the laboratory with a very unnatural process. They can get maybe 200 nucleotides before something's going to go wrong. And the longer you make it, the more chance, oops, there's a mistake there. And then you have to throw the whole thing out and start over again. So it's quite difficult to make, even with our modern technology.
So there is, in other words, there is nothing in the chemistry of the molecules or atoms involved now when it comes to DNA, or of the different components involved, that would dictate the linkage that we'd find along the DNA ladder.
Exactly. Exactly. Otherwise, you could claim it was a natural process because there's a preference to form it exactly the way it. No.
Gotcha.
Not at all. Like I said, even the greatest of scientists today will struggle very much to make these long, perfectly arranged molecules.
In the statement we were looking at there about no way to scientifically investigate the question of a designer, 2 sciences I can think of know how to look for intelligences. And those 2 sciences would be archaeology and what we might call a branch of astronomy called SETI, Search for Extraterrestrial Intelligence. In archaeology, an archaeologist or an anthropologist may pick up a chipped stone from the ground and ask himself, how did this stone come to be chipped? Was this stone chipped because it fell from that cliff up there and bounced off a few rocks on the way down? Or it was lying in a stream and water freezing and thawing perhaps in the winter has chipped off some stones? Or was it carefully chipped by a workman who was working on it? Well, if there's only 3 chips off the thing, you probably can't tell. But if there are 100 chips off the thing, and those 100 chips are aligned in such a way that they make a pretty good arrowhead or spear point, I think you can feel quite confident that you are looking at evidence of an intelligence behind it. The placement of 100 chips on the surface of a axe head or spear point or arrowhead is a good indicator that that is not merely something that happens to look like an axe head, spear point, or such, but that it really is such a thing. Well, how much information is the placement of 100 chips? Well, it's 100 triplets locating that in 3 dimensions, let's say relative to the center of gravity of that particular piece of rock, if you like. So it's about 300 pieces of information, or if you think of a couple decimal places, you could run it up a little further, but it's like that, all right? How would a person searching for extraterrestrial intelligence tell whether signals coming in from outer space through a radio telescope antenna, whether they are little green men or whether they are pulsars rotating very rapidly? That was a question that arose to Jocelyn Bell and Stanley Hewish when they were first looking at the pulsars when they were discovered. And the answer, I think, would be you would examine the signal, and the placement of perhaps 100 or 200 or 300 signals would tell you whether it might just be some kind of rotation phenomena, or whether it looks like what we might call the organized complexity that is more characteristic of a language. Carl Sagan, in his science fiction novel Contact, investigates this particular question again. It would seem then that perhaps 100 or 200 or 1,000 pieces of information, digits of information, bytes of information, would be enough to tell whether you're looking at something random or whether you're looking at something that is real, intelligent, if you like, or an intelligent designer lies behind it. Interestingly, the most complicated thing we know of in our universe is life. And the information content of even a simple E. coli bacteria, it's a prokaryotic cell, not a complicated one, etc. Sagan says in his article Life in Encyclopedia Britannica, the information content is equivalent to 10 to the 12th power bits, or about 100 million pages in the Encyclopedia Britannica. And it's not just random stuff. It's making a working machine. That sounds to me like we are getting a message from E. coli that it was designed, and that a person who claims that anything else is happening is under a certain obligation to show how such a thing could have designed itself. And not just by waving hands, but at least by some kind of computer simulation that you can get from the kind of information content in simple molecules up to the kind of information content of 100 million pages in Encyclopedia Britannica by random processes, even though constrained by natural laws.
With computer animation, we can enter the cell to view this remarkable system at work. After entering the heart of the cell, we see the tightly wound strands of DNA, storehouses for the instructions necessary to build every protein in an organism. In a process known as transcription, a molecular machine first unwinds a section of the DNA helix to expose the genetic instructions needed to assemble a specific protein molecule. Another machine then copies these instructions to form a molecule known as messenger RNA. When transcription is complete, the slender RNA strand carries the genetic information through the nuclear pore complex, the gatekeeper for traffic in and out of the cell nucleus. The messenger RNA strand is directed to a two-part molecular factory called a ribosome. After attaching itself securely, the process of translation begins. Inside the ribosome, a molecular assembly line builds a specifically sequenced chain of amino acids. These amino acids are transported from other parts of the cell and then linked into chains often hundreds of units long. Their sequential arrangement determines the type of protein manufactured. When the chain is finished, it is moved from the ribosome to a barrel-shaped machine that helps fold it into the precise shape critical to its function. After the chain is folded into a protein, it is then released and shepherded by another molecular machine to the exact location where it is needed.
This is absolutely mind-boggling to perceive at this scale of size such a finely tuned apparatus, a device that bears the marks of intelligent design and manufacture. And we have the details of an immensely complex molecular realm of genetic information processing. And it's exactly this new realm of molecular genetics where we see the most compelling evidence of design on the Earth.